Hello, I'm here in Cambridge in the community orchard close to Midsummer Common, and I'm very excited about this video I'm doing to explain a very interesting topic of C++, which is type erasure. Type erasure in C++. And I will try to help you understand what it is by coding stdn from scratch. Actually, I will split this video in three parts. The first one is an introduction where it will not be long. It's this part here where I will talk about why I've chosen stdn, what type erasure is and what it is not, because by the term type erasure, without qualifying it with C++ before it, something else is sometimes intended. And then I will give a few examples of, if you want, type erasure, but also something else that is not generally referred to as type erasure, even if it's shared with type erasure, the two main aspects of it. And then in a second video I will implement stdn from scratch, and that will take a bit longer. And finally, in a third video I will make a few observations about stdn, at least all those that I will not have made along the way of implementing stdn in the second part of the video. And in the third part of the video, the observations are listed there already, and I will go over those. By the way, I'm not encouraging the use of stdn because overusing it and even just using it is generally a bad sign, in the sense that you should always strive not to use this abstraction in your code base, because if you're going to use it, you're most likely introducing a design flow, and if you feel like you're really forced to use it because there is no other way to accomplish what you wanted, then maybe the point is that the code is flawed in the first place. So yeah, no encouragement about using stdn, but it is a good workbench for explaining type erasure. Indeed, why have I chosen it? Because it does use type erasure, obviously, but also because it is significantly simpler than its older friend, std function. Std function is older because it was introduced in C++11, whereas stdn was introduced in C++17. But it is much shorter, much easier to implement, because it has to do much less than std function. But I've linked a presentation by Fedor Picus, C++ Type Erasure Demystified, which goes through the implementation of std function and also presents a benchmark at the end of various possible ways of implementing type erasure for the purpose of implementing std function. So what is type erasure in C++? And first of all, why am I saying C++ type erasure rather than just type erasure? Because by type erasure, something else is meant in some fields, like in general, in type theory, in programming language design, type erasure means something else. And we're going to see an example of what that means with this code here in Godbolt. I've prepared this example. As you can see here, we have a class foo, which is just a container for an int. So it's just a wrapper to an int, essentially. And then I have two overloads of the function add. The function add, that in this case, this overload here takes two ints and gives back an int, and this one takes two foos and gives back a foo. It's not the policy, the argument passing policy is not important. I could pass by value or by const reference, doesn't matter. The whole point is that these two functions are doing a very similar job. One is adding two ints, and the other one is adding the two ints inside of two foos and then giving you back a foo. And the point is that these two functions are different because they have a different signature, even if at the end they are doing a very similar job. And the fact that the types are different helps the compiler tell you if you're calling them the wrong way or the right way. So down here I'm calling this add with two foos, and the code compiles and it does what it is expected to do. In this case here I'm calling it with two ints, and the compiler is compiling this code and is doing the right thing. So the first call is resulting in calling this function, and the second call here is resulting in calling this function. And everything is fine. But if I try to call add with a foo and an int, then the compiler will error out, and it will tell me something along the lines of no known conversion, this line here, no known conversion for argument 2 from int to foo. Or if you want, when it tries the other overload, it says no known conversion for an argument 1 from foo to int. So one way or another, like the compiler is trying the two overloads and none of them is actually viable. So that's to say that the types are doing their job. Like the compiler knows about the types and it is accepting or rejecting the code accordingly. So the types are there when the compiler compiles the code. But once the compiler is type checking the code, but once the compiler is happy once the compiler has made sure that the types are correctly used, then it will compile these two functions, and in that phase it will throw away the types, it will erase the types. And indeed, as you can see here, this function here and this function here are compiled exactly to the same code. This is the code, this is not the code, this is just the name of the function, it's just a label to tell another part of the program where they have to jump to if they want to execute this function. But the function is just these 3 lines, which are exactly the same as these 3 lines, which are those for this other function here. And so the types have been erased in the sense that this doesn't contain a type int and this doesn't contain a type foo. The fact that the numbers to be added up are ints is built into what operation is being used to add these two things. But again, that's the same here and that's the same here. So this is what it's meant by type erasure in type theory and in when we talk about programming languages in general. But that's not what we're talking about. We're not talking about this. We're talking about C++ type erasure. And this excerpt here is from the book the C++ Programming Language from Bjarne, the creator of C++. And this basically refers to the emergence of the term type erasure as a name for a technique of using a single runtime representation for values of a number of types and relying on the static type system to ensure that they are used only according to their declared type. What does this mean? It means that type erasure consists of 2 parts. One part is the erasing of a type at compile time. So you're cutting away the type from an object and throwing that type away in such a way that you can have multiple objects you can deal with multiple objects that originally have different types, different and unknown types, and you can deal with them through the single runtime representation. In the case that we will look at, that is std_any. Std_any is that single runtime representation. It's just std_any, and we use it to deal with multiple different types, different and unknown types. But once we erase the type, what can we do with those objects? Once we've forgotten about their types, we can't do anything, because after all, the type is what tells us what are the member functions, for instance, of a given object. If we don't know about the type of that object, we cannot call the member functions. And indeed, that's the second part of type erasure, which is recovering the information of what the type is at runtime. That means that you want to be when you erase the type, you want to make sure to put things in place such that at runtime you will be able to recognize the object that you've erased the type of, and that you can use the API of the type it was declared with, so that you can, for instance, extract that original object from within the type erased container, such that you can make copies of the original object, and clearly that you can destroy it when it goes out of scope or it is destroyed somehow. And then more in general, that you want to make use of the original object of all its API. You want to be able to do this. So let's look at a few examples. Well, the last example is std_any precisely, but I will first give kind of an introduction for it. So the first example is shared pointer deleter. Why is that the case? Both unique pointer and shared pointer allow you to pass in a deleter which is a function. For instance, this is a deleter here, which is a function that takes a pointer to the pointee of the unique pointer or the shared pointer, and has the responsibility of deleting that object. In this case, I'm just calling delete. This is exactly what the default deleter would do, but the point is not what the deleter does in this case. The point is that we can pass the deleter to a unique pointer as well as to a shared pointer. But the way it is passed to the unique pointer is via the type. Like, we pass the deleter, actually the type of the deleter, as part of the type, as a template argument to the unique pointer. So it becomes part of the type. And indeed, like, these are the types. up1 as type unique pointer of int, and up2 as unique pointer of int, comma, another type. You can ask the IDE and it will tell you that. This is not unique pointer of int. This is something else. It's unique pointer of int, comma, another type, the type of the deleter. So these are different, and this static cast here is telling us, yes, they are different types. So that means that when you construct a unique pointer with a deleter, it will store that the deleter, and clearly, in order to store the deleter, that could be a lambda, could be a free function, could be a pointer to a function, the unique pointer has to be templated on that type. At least, it's not that it has to, but that's how it is designed. So there is no type erasure here. The type of the deleter ends up being part of the type of the unique pointer. But that's not the case for the shared pointer. When you want to pass the deleter to the shared pointer, you do it by passing it to the constructor. Whereas the type of the shared pointer stays the same. This is a shared pointer to int, and this is a shared pointer to int as well, even if the deleter is different. Yet, when these two shared pointers go out of scope, this will call the default deleter on the int object, and this will call instead the provided deleter. So somehow the two shared pointers, even if they have different types, they are keeping memory of what the deleter is that we've passed or not passed. How can these be achieved? Via type erasure. Like in the insides of shared pointer, you can go look at it and you realize that somehow the shared pointer will manage to lose track of the type of del here, the actual type of del, but it will still make the code of this deleter available through another runtime representation, which is unique for this deleter and for any other deleter with the same signature. So this is just to give an example of another example of the presence of type erasure in C++, the usages of type erasure in C++. Another thing which is not usually referred to type erasure is the mechanism of inheritance and virtual dispatch. In this example here, what do I have? I have a struct with a virtual method and a virtual destructor, and this is going to be used as a virtual base class. And then we have two derived classes. And then we have, and each one of those two derived classes overrides the work member function somehow. I haven't included the definitions because that's not important for the purpose of this explanation. But then we have a function here called getDerived, which takes an int and it returns either an object of type d1 or an object of type d2, depending on the value of the integer. If it's 1, d1, otherwise it's d2, but it returns them via a unique pointer to the base class. That means that once you call derived, you don't actually know statically whether the object pointed to by the returned unique pointer is a d1 or a d2. In this case, you know it because you see the code. So down here, for instance, I'm declaring a vector of unique pointers to the base class, and then I'm pushing back the value returned by getDerived called with 1, and then pushing back another value returned by getDerived 2. And so you say, oh yeah, the first one is d1 and the second one is d2. Fair enough, but remember that this function could actually be defined somewhere else in another translation unit, in another CPP file, and linked against this one. And in that case, you wouldn't know. You wouldn't know what the body of this is. You wouldn't know what it does. So it could return through the unique pointer to the base class, it could return an object of the base class, an object of one of these two derived base classes, or even an object of another derived base class defined somewhere else. You don't know. So this is the function that is erasing the type. This is the function that is returning an object of a class, for instance D1 or D2 or B or whatever derived from B, but it is returning it through a pointer to the base class. So the information at compile time of what the type of the pointee is lost, is erased. So that's the bit that does kind of the type erasure. And what about the type recovering? Well, that happens when you actually try to call a member function on the objects. When you do this call here, it doesn't matter the fact that this object v square brackets of 0 is held by a unique pointer to the base class. The call to work will be dispatched to the version of work overridden by whatever class that object is of. In this case, we already know, well, or at least in this case here, in the case that this code, I've just deleted this somewhere else, compiled and linked against this one, we know that this will be D1, this will be D2, and so this call here will dispatch to this overload here, sorry, no overload, this override here, and the other one to this override here. So to some degree, this is a bit similar to type erasure, with this function being the one that erases the type by returning a pointee of a more specific type through a pointer to a less specific type, whereas the call to the member function through a pointer to the base class will actually recover at runtime the type of the actual object and call the member function for the class of that actual object. But this is happening without you doing anything. This is just how the language works. And so you don't have to do any extra work. On the other hand, when we will implement std_any, we will see that we actually have to put effort into doing it. And in which sense does std use type erasure? Well, we want to be able to write some code like this, right? Where we initialize an object of type any with an object of type foo, whatever the type foo is. And so this is the place where the erasure happens, because after this line we've lost track of what is in this f. We don't know statically. We cannot take this object f and ask, give me your type statically. Like we cannot write a static cast telling the type inside of the object inside of f is such and such. Precisely because this is expressing the idea that f can change type at runtime. So the erasing happens on this line, and the recovering of the information happens on this line, where I'm saying, actually, I know that in that f there is a foo, so please give me back that foo, and then I can operate on that foo with its original API. In this case, I'm doing .i to extract the integer that is inside of foo. Foo is just a wrapper to an integer, more or less like the one I showed earlier. So yes, so this is the first part of this presentation, and the next one will be actually implementing std_any. I hope you enjoyed this one, you understood a bit more, something about type erasure, but definitely on the next video when I will implement std_any from scratch, that should clarify any doubts whatsoever on what type erasure in C++ actually means and what are the main ingredients to implement it. Thanks for joining me, and I hope you will also join me in the next video. Bye.